Hello and welcome back. Today we're talking about theorems. So a theorem is a logical truth. Um, it's a sentence that is always true no matter what the atomic statements mean. We've seen these types of statements under a different name, tautologies, um, when we are trying to prove a theorem, um, or when we're trying to state that something is a theorem. What you do is you put the therefore sign for it without any premises. So here we have therefore, right? P then not P then P, sorry, that's a theorem, right? It should be kind of obvious that's logically true. If P, then P, right? So that's how you would write if P, then P is a theorem. You put the therefore sign and then the statement. So proving theorems, you can't use a direct derivation because there are no premises, right? It's just therefore and then the statement, right? So how do you prove a theorem is true? Well, you can use conditional or indirect derivations because those types of derivations give you premises, right? You get to assume some things. And so if you're proving a theorem, you'll be doing it using a conditional or an indirect derivation, depending on the type of statement that you're dealing with. So if we wanted to prove if P then P, well, that's a conditional statement, right? So we'll use a conditional derivation. We'll assume P. Um, anytime you have a statement, you can always rewrite it on another line, and that's a rule called repetition. We haven't had any need to use it yet, I don't think, but you can always just, if you got P on line 1, you can write it again on line 2 or any other line, and you can just put repetition as your justification. So we've assumed P, and now that's the antecedent. We've now got the consequent just by repetition, right? So we can close out our conditional derivation and say if P then P. So that's a very simple proof of a theorem, right? Of a very simple theorem, but it is a theorem. And now we're going to get into some slightly more complicated, but also more useful theorems. So once you've proven a theorem and you've proven that it's a logical truth, you can use it in future derivations. It becomes a rule of inference. And that's nice. You can build up a library of theorems, right? Once you prove a theorem, now you've got a new rule, and you can just use it as a rule, right? You've already done the proof. You know that anytime, you got P, you can conclude P. That's basically what the theorem we just proved meant, right? So you could use that if you ever wanted to. Um, and you can then use those rules to derive other rules and so on, right? So we can build up a library of new rules, and really it's infinite the number of new rules you can create. So here's one. If Q, then if P, then Q. So this is a theorem of logic. It's called implication. Let's go ahead and prove it. Let's see if we can prove it. It's a conditional, right? So we would want to assume the antecedent, which is Q. Now, since the consequent is also a conditional, we can do a conditional proof within a conditional proof. So we indent a little bit further, and now we assume the antecedent of the second conditional. So we assume P. What are we now trying to prove? Well, the conditional we're currently trying to prove is if P then Q, right? That second conditional. So we're trying to get to Q. Well, we already have Q from line 1, right? So we can just do repetition. Now we've proven that second conditional, if P then Q, and that happened to be the consequent of the original conditional we were trying to prove, right? If Q, then if P then Q. So we've just finished our original conditional proof, right? So often you'll see this in proving theorems. They will be true conditional proofs, inside conditional proofs, maybe an indirect proof inside a conditional proof. So you may end up indenting multiple times, doing proofs within proofs within proofs, right? But take a look at that one and convince yourself that it makes sense, right? We had a conditional, that was our original theorem, so we assumed the antecedent on line 1, that was Q, and then we realized that the consequent that we were trying to prove was also a conditional, so we'll do another conditional proof. So that's when we assumed P, right, which was the antecedent of that conditional that was the consequent of our original one. I know this is my job, saying terrible sentences like, it's the antecedent of the conditional that was the consequent of the original conditional, right? But hopefully at this point in the class, that terminology is starting to be familiar. I've been trying to encourage you throughout the course to get that stuff to be second nature in your brain, right? So again, line 1, we assumed Q. Then we saw, oh, we got another conditional, so we'll assume the antecedent of that, which is P. Then we just needed to find the consequent of that conditional, which was Q. We already had it on line 1, so we just did repetition. Okay, that inner conditional derivation is done, right? We've proven P then Q. And in doing that, we actually ended up finishing our original conditional derivation because that was the consequent we were trying to show in the first place. So we finished it. So now we've proven the theorem called implication, if Q, then if P, then Q. So what this means is anytime you've got a statement, that can be turned into a conditional with that statement as the consequent, right? So now you can use implication as a new rule of inference. So we'll use the abbreviation IMP for implication. So suppose you had a proof like this. You've got Q as one premise. You've got if P then Q then S as another premise, and you're trying to prove S. Well, you could solve it like this. Right, line 3, you could use implication from line 1. You got Q, right? So I can create a conditional with Q as the consequent. And I can put anything as the antecedent. It could be P, it could be R, it could be something more complicated. Instead of Q, we might have something more complicated. We could still create a conditional with that as the consequent, right? So here P and Q could stand for anything, but here we're doing the simplest version. So again, I started with line 1, I used implication to create line 3. And now that I've got that conditional in line 3, I can just do modus ponens to get S from lines 2 and 3. So that's how you might use implication in a proof. I'm going to prove for you two of the most useful theorems. The first is called De Morgan's law, right? And what De Morgan's law does is it allows you to convert conjunctions into disjunctions and disjunctions into conjunctions. Now, it's not super straightforward. You can't just turn P or Q into P and Q, but it involves some negations. So this is the De Morgan's law. It says if you got a negated conjunction, so not P and Q, you can convert that to a disjunction where each of the disjunctions is negated, not P or not Q, and vice versa. So if you've got the disjunction not P or not Q, you can turn it into not parentheses P and Q. And as we'll see, sort of any combination thereof, right? So well, we'll get to that later. But let's prove it, right? So I'm going to walk you through the proof because it's pretty complicated, right? So it's a biconditional, right? So we're going to want to prove two conditionals and then join them together, right, with biconditional. So we'll have to prove if not P and Q, then not P or not Q. And then we'll also have to prove it the other way. The other way is actually a little easier to start, so let's do that. So let's start with the right biconditional, not P or not Q, and let's see if we can derive the left biconditional, not P and Q. So I'm going to try to prove not P and Q by indirect derivation. So I'm going to indent, do another another subproof, right? So I'm going to assume P and Q, which is the negation of that left biconditional there, and see if I can get a contradiction. Well, I can certainly, anytime I see a conditional, usually I'm going to try to simplify that out. So I can get P by simplification from line 2. I can get Q by simplification from line 2. Now with line 1, that means I can get not Q with ds from 1 and 3, right? Because 3 is the negation of the left disjunct of 1. And now that I've got not Q, I've got a contradiction. Oh, Technically, probably should have put another line that explicitly says Q and not Q. But I found my contradiction, right? So I can negate line 2, and now I know that that is true. We're still within my original conditional proof, but we've just closed out the indirect derivation. So now we're back to our conditional proof, and that was not P and Q was the consequent I was trying to prove. So I've just finished my conditional proof, and my justification would be 1 through 6 conditional derivation. So I've proven one of the conditionals. I need to prove the other conditional, right? Now I need to prove if not P and Q, then not P or not Q, right? And so I'm going to use the same technique. I'll start with an assumption, right, for conditional derivation, and then to prove the consequent, I'm going to assume the negation of it and try to prove it that way by finding a contradiction. So let's see. I've got not, parentheses, not P or not Q. I'm going to try to show that their contradiction follows. Now I'm going to do another indirect derivation. I told you the first conditional we had to prove was a little simpler than the second one. The second one I have to go a couple derivations deep. So I'm assuming not P. And so with addition, I can say not P or not Q, right? Now I happen to have the negation of that on line 9, right? So with conjunction introduction, I'll make explicit that contradiction that I've just produced, which means that P, right, is the case. I can assume the I've proven, right, that 10 is false by deriving a contradiction. So now I've got P. Okay, what am I going to do with P? Well, you may have noticed, right, what I'm going to try to do is prove the negation of 8, right? I've got P, I just need to get Q, and then if I can get P and Q, that's the negation of 8, right? And that will be my negation, that will be my contradiction that I can use to prove 9. So I'm assuming, should be assuming not Q, and once again, with addition, I get not P or not Q, and that is the negation of 9 there, right? So we'll make that explicit. And so now I've got Q, then direct derivation. So now I can put P and Q together with conjunction introduction, and that is the negation of 8, right? So let's make that clear, that we've got a contradiction here. And therefore, finally, my assumption 9 is proven false, and so I've got not P or not Q, which was the consequent of the original conditional I was trying to prove. So if not P and Q, then not P or not Q. Now that we've proven each conditional separately, we have De Morgan's law, right, which says if you have a negated conjunction, you can derive a disjunction where each of the disjuncts is negated, right? So now conjunctions can be turned into disjunctions, but it's in a specific way. It's not just P and Q becomes P or Q, right? But if you have a negated conjunction, you can turn it into a certain kind of disjunction, right? Where the disjuncts are negated, and vice versa. That was a gnarly proof. I wouldn't expect you to be able to do that proof on your own. Hopefully, be able to walk through the steps that I did, and hopefully each step will make sense to you. If you get lost on any of those steps, let me know, or come to office hours. But I just wanted to give that to you. Now you have De Morgan's, and you can use that anytime you want, right? If you run into a negated conjunction, which can come in handy in indirect proofs, right? So if I'm trying to prove a conjunction, and I might, in an indirect proof, assume it's negated, now I can turn that into a disjunction that then I can work with, right? So it comes in handy, and vice versa. And in fact, there is another version of De Morgan's law that I won't prove for you, but you're welcome to use, which is if you see a negated disjunction, you can turn that into a conjunction with each of the conjuncts negated. So it works the other way too. I didn't prove that version of it, but you're welcome to use it. So, here you have a disjunction. You could use De Morgan's, this one is T or not P, right? So here, not both of the disjuncts are negated, but that's okay. I can turn it into this conjunction. It's a negated conjunction where, notice, each of the conjuncts is the negation of the disjuncts that it came from, right? So T becomes not P becomes P, right? That's a valid use of De Morgan's. So it's not always as straightforward as P and Q becomes not P or not Q, right? If you had, again, P and not Q, that would become not P or Q, right? So the negations, again, Q is the negation of not Q is the negation of Q. So it's very flexible in that way, right? Here's another example. Here we have the negation of this conjunction P and if S then T, right? So the right conjunct here is not atomic, it's a conditional. That's okay. You can still use De Morgan's. You would get not P or not S then T. Right? So the problems I'll give you will be relatively straightforward, simple applications of De Morgan's, but I want to give you a sense of how broad the applications are. Right? You can use it for a lot of stuff in a lot of ways. So I'm going to give you one more theorem that's super useful. There's so many theorems. We won't spend, this is the last part of, we're not going to spend a lot of time on this, but I want to introduce the concept to you and give you a couple super useful ones. So this one is called conditional disjunction, or CDJ, and it allows you to turn any conditional into a disjunction and vice versa. Now, once again, it's not as simple as like P then Q just can become P or Q. There's some negations involved, as we'll see, but still very useful. So here is a conditional disjunction, or CDJ. It says if you've got a conditional P then Q, that can convert to the disjunction not P or Q. See, so the antecedent of the conditional becomes negated when you turn it into the disjunction. The consequence stays the same, and you can go either way, right? From the conditional to the disjunction, from the disjunction to the conditional. You might have some different arrangement of negations, right? So if your conditional was not P then Q, that would turn into the conditional, or sorry, the disjunction P or Q, right? And so on. But let's prove it. So note the disjunction you get has one disjunct negated, right? So yeah, it's not as simple. Don't think that you can turn any conditional just into a disjunction without making some slight changes, right? So this is a theorem takes a little time. I'm going to start on the next slide, and we'll jump into it. We will use DM to prove this theorem, right? So once you've proven a theorem, you can use that to prove other theorems, and that's how they build up. So these theorems are like powers you can unlock, right, to use in further proofs and create further theorems and so on. So we'll see how it works right now. Okay, so we're trying to prove CDJ, right? So it's a biconditional, which means we're going to prove two conditionals separately and then join them together, right, with biconditional. So let's start with this one. We'll assume if P then Q, and then we're going to try to prove not P or Q. Right? So as I did with both of the conditionals in DM, I'm going to try to prove the consequent with an indirect derivation. Right? So here we have a negated disjunction, and I can use DM to turn. Now this is the other version of DM that I didn't give you, but or I didn't prove for you, but you're welcome to use, which is any negated disjunction can be turned into a conjunction. You just have to swap the signs basically on each of the conjuncts. So you see how that happened here. We started with not parentheses, not P or Q. Using DM, we can turn that into a conjunction where not P becomes P and Q becomes not Q. Okay, so now we've got this conjunction. What do we do with it? Remember, we're in an indirect derivation here, so we're trying to produce some sort of contradiction. So let me simplify that conjunction out into its parts. So we've got P from simplification from 3, and we've got not Q simplification from 3. So I'm just going to do modus ponens with line 1 and 4 and get myself Q, right? And that's a contradiction with line 5. And so I've got my contradiction here, line 6 from conjunction introduction. And now I can close out this indirect derivation and say, yes, I get not P or Q. And that was the consequent I was trying to show, right, from line 1. And so I've just finished my conditional derivation as well, and we've proven half of the theorem. So let's try to prove the other half. So now we're going to assume not P or Q, and we're going to try to prove if P then Q. That's a conditional, so actually I'm not going to use an indirect derivation this time. I'm just going to assume P, right, and try to get to Q. So I've got a conditional derivation in my conditional derivation. Well, I get to Q pretty easy with ds, right, from line 10 and 11. So now I'm done. I've proven the consequent of the conditional we're trying to prove. And so now we've proven both conditionals, so we just have to glue them together with biconditional, and we have proven CDJ, or conditional disjunction. Anytime we have a conditional, we can turn that into a disjunction where the antecedent of the original conditional becomes negated, right, and becomes the left disjunct of the new disjunction, and vice versa. I can turn any disjunction into a conditional. So that's what I just said, right? You can turn any conditional into a disjunct where the left disjunct is the negation of the antecedent of the original conditional. I know that's a mouthful, right? Hopefully this point in the course, you've got your bearings with this terminology. And you can turn any disjunction into a conditional where the antecedent is the negation of the left disjunct of the original disjunction. Notice the consequent of the conditional just becomes the right disjunct and vice versa. That one doesn't get changed, right? It's the antecedent gets negated when it turns into a disjunction, and the left disjunct gets negated when it gets turned into a conditional. So you're really only messing with the left part. So some examples of CDJ. So if I had the disjunction P or Q, now none of it is negated, that's fine. I can still use CDJ. I could create the conditional not P then Q. If I had this conditional, if Q then not S, right, I can certainly turn that into a disjunction. It would be not Q or not S, right? So notice in each case, it's the left part that gets negated, the right part stays the same. One more, right? So this works even if your antecedent is not an atomic statement, right? So here the antecedent is a conjunction, that's fine. I can still turn it into a disjunction, right? The left disjunct is the negation of P and Q. So that's how CDJ works. Let's do a little practice. So again, I wouldn't ask you to prove CDJ on your own, but now you have it. That's a rule you're allowed to use. Right now, after this lecture, you're allowed to use implication, you're allowed to use De Morgan's, both kinds, and you're allowed to use CDJ. So let's use those in some proofs. And then the homework is, very simple. I'll give you a couple theorems to prove on your own that are, very simple, not as hard as these ones. And I'll give you a couple derivations where you'll need to use these derived rules to solve them. So let's practice that a little bit. So yeah, implication, De Morgan's, and conditional disjunction are now in your library of theorems. You can use them. Let's practice that. So here's a proof. So you've got premise 1, not P and Q, premise 2, P, and you want to prove not Q. Well, now that we have De Morgan's, right, we can change 1 into not P or not Q. And now that I have that disjunction, it's easy to get not Q on its own, right, with ds from line 2 and 3. And so now I've proven it, right? So this would have been maybe impossible. Maybe you could have done it with a long indirect derivation or something like that. But now that you have De Morgan's, it's pretty straightforward to solve this proof. Let's try one more. So here we have a conditional, if P then Q then S. We have a disjunction here, and we're trying to get S on its own. Well, you may look at line 2 and say, oh, with conditional disjunction, I can turn line 2 into if P then Q, which happens to be the antecedent, right, of 1. So then I can just do a simple modus ponens and get S on its own. So it takes a little while recognizing the opportunities to use DM and CDJ. Again, I'm going to give you very simple stuff, and we're not going to go too deep into doing long, complicated proofs where you have to know all these, how to use all these rules. I just want to introduce you to the concept and see how, you can sort of extrapolate what logic looks like in, maybe the next logic class you take, right? Where you have this whole library of theorems, so many different new derived rules that you can use. So that's it. Practice the homework and come see me in office hours if you have any questions. And again, nothing's going to be as complicated as those proofs I just walked you through. I just want you to know the concepts here.